Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this video, we're going to just spend a brief few moments talking about derivative notations. There are a lot of different derivative notations. These are the four most popular derivative notations, but it's important that you get used to at least 3 of these 4. And by the way, 2 are required, and then the other 2 are kind of like, they just depend upon where you're going. So let's talk about the one that we've seen so far in our lecture series. Lagrange's notation. So each of these people in this list were essentially very famous mathematicians, are very famous mathematicians and physicists. And Lagrange was the first one to create this notation of using the prime on your function to indicate you're taking a derivative. So somebody gives you a function f, we needed a new notation that showcased we're taking its derivative, so we used f prime. And that is actually a very simple, nice, beautiful notation. You can also write that Lagrange notation in other forms, like some people use f prime without the of x. That's perfectly fine. Some people, because y is actually equal to f of x here, some people will write y prime. That's perfectly fine as well. There's nothing wrong with that. You would not be wrong if you wrote that. Or they'll write y prime of x. That's also perfectly fine. All 4 of those are acceptable. The most powerful of those forms is the very first one. That's just the most accurate, I suppose. The rest are notational shortcuts, but they're all still universally accepted. The next one in the list, so that takes care of this guy, number 1, Lagrange, is Leibniz. Leibniz notation is really, really powerful. Very popular, also incredibly confusing. It's incredibly confusing only because it's the first time you're seeing it and it looks weird. So I'm going to show you how to read this. So let me write this down. And I'm going to stop right there because I want to show you how I read this, because this is just important. So this fraction looking thing is not a fraction at all. It's an operator. Just like this, well, that's a terrible notation, but there we go. That x there is no longer an x, it's a multiplication sign, right? Or better yet, actually, that's probably too confusing. So just like this sign right here, that is not dot divided by dot. Even though it uses the same looking type of script, we know what that is. It's a division sign. It's a division operation, right? So nobody says, hey, I saw that you handed me 12 times a fraction with dot divided by dot. Well, dot divided by dot, since it's the same picture, is 1. So I'm right when I told you the answer is 72, right? No, no, the answer is 2. You're just misreading the notation. This notation here is not a fraction with a dot on top and a dot on the bottom. It is a shorthand notation for division. It's actually a longhand notation, to be honest with you. Okay, so that all being said, those are called operators. Well, this picture, d dx is what we'd call it, d dx, that is also an operator. And it just tells us we're taking the derivative of whatever's going to follow that operator with respect to x. So we'll talk about the with respect to x in a moment, but let's fill in the derivative of. So the derivative of y with respect to x. That's what dy dx stands for, the derivative of y with respect to x. It is also commonly written this way, the derivative with respect to x of y. It means the same thing. Let's see, is there other ways that I have it written here? Okay, yeah. If you have f instead of y, if that's what you prefer to use, then you could say it's derivative of f with respect to x, or again, derivative with respect to x of f. Some people will use parentheses after this. It's perfectly fine. Now, here is why Leibniz notation is actually more useful than the Lagrange notation. If you're planning on being successful in calculus, and if you're planning on moving through physics or chemistry, biology, engineering, you're going to deal with multivariable problems that don't just have an x and a y, but they have y as a function of 4 variables, right? So you could imagine that, for example, I'll do it this way. The temperature in your room is a function of, let's say, the outdoor temperature. Maybe I should call that T sub O for the outdoor temperature. T sub I for, little t for the time of day. H for humidity. We'll just keep E for elevation. All right, so at least those 4 variables play into the role of the temperature in your house. Okay, so the temperature in your house is a function of at least those 4 variables. Now, if you want to know how quickly your temperature is changing with respect to one of those variables, you cannot just say take the derivative, because then people will just stop and pause and say, I don't even know what to take the derivative of and with respect to. Like, it's very, very difficult. So actually, let's put a pin in that, and I'll give you a good example. If I said here's a curve, that's a 2-dimensional curve, isn't it? So it's like x versus y. Okay. And if I said I want to know the slope of that curve at a specific moment, remember what I said in a previous lecture, there's no such thing as a slope of a curve. There's a derivative of a curve. So if we want to know what's the derivative of that curve at a moment, you take its derivative and you find out, the derivative is just, pretend f prime of whatever this number is -2. Let's just pretend. Well, that's pretty easy if you're in 2 dimensions. But that's not the world we live on. So instead, pretend as though you're on a mountainside. So you're in a 3-dimensional space. And let's say that you're hiking up one of these mountains right here. And you're standing not near the top, but maybe on a trail that's along the edge or the rim of one of these peaks. And somebody says, what's the slope? That question is not answerable because it just depends upon the direction you're facing. If you're looking straight at the mountain, the slope is pretty steeply pitched. If you're facing away from the mountain, it's steeply pitched in the negative direction. If you're facing along the trail, it's probably a slight pitch. So it just depends on the direction that you're facing. So if somebody says, hey, what's the derivative? You have to say, are you talking in terms of the X direction, the Y direction, the Z direction, or some other direction? Like, there are so many different directions you could face. The slope changes just depending upon how you turn your body. The pitch of the mountain, the slope of the trail, all that stuff changes just depending on how you turn. And that is hopefully to convince you that when you have a multivariate problem, when you have more than 2 dimensions, but you have 3 dimensions or more, that asking for slope becomes, or derivatives, becomes kind of a pointless effort. Unless somebody is smart enough, Leibniz, to say, you know what, here's the big deal. I want you to take the derivative of your function, but with respect to h. Now I know I could take the derivative of this. I'll hold everything else constant, and I'll just look in the direction of h. And I'll say, how quickly is the temperature changing with respect to humidity? And that's why Leibniz, his notation is pretty awesome. Or Leibniz, actually. Anyway, his notation is pretty awesome because built into his notation is a reference to what variable you're taking the derivative with respect to. Now, all of that should pretty much fall on deaf ears right now. You should just say, what? What is he talking about? And that's totally fine. But I want to convince you that this notation is so powerful, it's not going away. It's going to haunt you. So you have to get used to it because it'll carry us forward through a lot of mathematics. But I do want to write in that little warning that d dx is not a fraction. It looks like one, but it's not a fraction. And if you say, but it looks like one, I'll just say, well, this is also not a fraction, right? So it's just important to realize that you have faced things that most novices would say, that looks like a fraction to me. And you are experienced enough to say, yeah, but it's not, right? It's just not. Just like this, people would say is a period. And you say, no, it's not. It's a multiplication sign. It just depends about it's all about context. So be very careful with that. Sort of decent examples actually for making them up on the spot. All right. The last two notations here are not as popular in Calc 1 and Calc 2. They become more popular once you get into differential equations. So if you're going into engineering and electronics, these start to kind of play, and physics, they start to play quite a bit of a bigger role. So Euler's notation, Euler is a very, very, very famous mathematician, has beautiful formulas associated with him. But his notation is somewhat simple. df of x means derivative of f of x. There you go. He also has that subscript notation to say, well, kind of like Leibniz did, what if we want to take the derivative of f of x with respect to x? So you won't see that in this course or in your course, maybe, but only once. So don't really sweat that. And then Newton's notation, that's for physicists. So Newton loves the dot notation. So y dot just means the first derivative. Now, I say the first derivative because we will actually venture into higher order derivatives later on, fairly soon actually. But that's Newton's notation. Note there is a weakness with Newton's notation. It does not tell you which variable you're taking the derivative with respect to. So Newton's notation works great in 2 dimensions, but once you hit 3 dimensions, all bets are off. That notation is kind of flawed. Just like Lagrange's notation at the top suffers from the same issue. You would never say, for example, f prime of xy. The reason why is then I need you to tell me which variable you're taking that derivative with respect to. So you would not say that. All right. So that's all this video was about, is to talk about just the different kinds of notations you'll see to make you less stressed. Calc 1 and 2 will focus on these two groups, right? Leibniz notation and Lagrange notation. And like I said, differential equations, which is like Calc 2.5, is going to focus a little bit more on Euler's notation. So, and actually Euler's notation and a teeny little bit of Newton's notation in that course as well.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.